No. Are you all in my class? Yeah. Yeah, sorry, it's not working. I have reported it, but not lucky there's room next door, but yeah, it's not working. So sorry about that. All right. Okay, so let's say what we're going to finish off this week is basically look at all the other types of integration strategies. The first one we went through was integration by inverse trig substitution. This one really powerful. Because this one, its sole purpose in life is to get rid of square roots that you can't handle any other way. Very powerful method. You can actually, although we're only going to use this one if we've got one of these three, basically an integral involving one of these three terms that a simple substitution's not working, not getting rid of, we can do this one. But you can actually use this one for almost any square root. You can sort of force it to work. A very, very, very powerful method. We're only going to use it for these three though, and as I said, this table is on the formula sheet and it tells you what to do. You've got a term like this that you can't get rid of, you use this substitution. All this column tells you is when you get rid of the square root, you are safe to always assume you only take the positive square root, you never have to take the negative. That's all that means, basically. And that you use this identity to get rid of the square root. And then to go back, you basically just use these little reference triangles and, what do you call it here, SOHCAHTOA or whatever you call it here, to go back to the x variables. So very, very, very powerful method, this one. The next method we did, there's two reasons I show this one, right? So firstly, because there are two integration formulas on the formula sheet that to prove them, I need this substitution. So if we recall on the formula sheet, the last page, we're going to end up being able to prove, not that I'm ever going to get you to do it again, it's on the formula sheet, it's given, but let's just say this one, for example, the integral of log of x and the integral of the inverse trig functions, these formulas, they come from integration by parts. Some of them are obvious, and the integrals of tan and cot are simple substitutions, but these two require this weird substitution. So there's two reasons I show this. One is because so I can convince you I'm not pulling these formulas out of thin air and show you where they come from. And two, that integration is tricky, right? And sometimes you need very, very weird techniques to handle certain integrals. And this is a weird one. This is a very weird one because you wouldn't initially assume this would work, right? But it does. Now, basically, I show it to you, we go through it, then we never talk about it again, right? So this one, I've never asked one of these questions, right? And let's be kind and say I ain't gonna, right? It's more just showing you that sometimes you have to be imaginative and to prove these two formulas. As I explained, this is a weird one. I call it the half angle substitution. Some textbooks call it the double angle substitution. Same freaking thing, of course. Half of one, double of the other, whatever. Right? But this is the substitution you do. Right? You let u equal tan of x on 2, which seems really weird. Right? Hence the term half. I call it a half angle because that's what you're doing. But some people call it double angle. I don't know why. You can write sines, so you use this one when you've got rational functions involving sines and coses where a simple substitution is not working. You can write sine and cos in terms of this new variable u, and then that's how you change your variable, that's your replacement for dx. And although it doesn't look like it, these actually let us do a wide variety of integrals. And I explain, this is how we prove the integral formulas of sec and cosec, right? So sec being 1 on cos, right? So I use this substitution, and I know now that sine becomes 2u on 1 plus u squared, and cos becomes 1 minus u squared on 1 plus u squared. And of course sec is 1 on cos, so sec is basically 1 plus u squared on 1 minus u squared. So you do that in your integral, you do your change of variable, and it will become this function here, right? Now, the next thing we're going to do is integration by partial fractions. You can write this as this. I'll explain that bit in a sec, right? That you can integrate. That's two really simple substitutions. And then you can use the log laws, write it like that, and to go back to x requires a fair bit of algebra, right? But you can show that sec plus tan is in fact 1 plus u on 1 minus u, and that's where the formula comes from. Right? As I say, the reason I show this one is you can prove the integration formula for cosec in a very similar way. Do it, it's fun. Right? But as I said, the main reason I wanted to show these is it's a weird one, right? And lots of textbooks don't cover this method. And there's a couple of reasons for that. One, it's weird. And two, if you go on in mathematics and you learn about, so we're doing multivariable calculus, but technically what we're doing is real variable multivariable calculus, right? So we're only interested in real numbers. You can do calculus on functions that take complex numbers as independent and dependent variables. It's called complex function theory. Very cool stuff. And doing integration with complex functions is actually easier than real ones. So though it doesn't seem intuitive, it is, because we have a famous result called the Cauchy residual theorem, which lets us work these things out. And what you'll learn then is if you have a nasty integral involving trig functions, it's actually easier to do it in complex space, right? So that's why some people don't bother with this method. But anyway, I do have a couple of examples. Feel free to do it, but I'm probably not going to ask one of these ones, to be honest, right? But there's a couple in here. You know, so for example, if I asked you to integrate this, notice the simple substitute, there's nothing that's going to work, right? And so basically, at this stage, we're stuffed. We do this very weird change of variable, and what this one will become, after a little bit of algebra, is the integral of 2 over u plus 1 all squared. So that's another simple, so if you let v equal u, that's basically 2v to the minus 2. Oh, that I can integrate. Right? And then you just basically replace the x, right? And another one there. If that was sine x on 1 plus cos x, then a simple substitution would work. You'd let u equal 1 plus cos of x, du on dx is minus sine of x, that's going to cancel with the top, done. Again, notice a slight change stuffs everything up, right? Making it a cos up the top instead of a sine ruins everything. Right? And this comes back to when you're doing integration questions, make sure, please, that you answer the question I've given you. If you stuff up a sign or a power or something, you could make your life very difficult, right? And end up with an integral that's impossible. So make sure you read the question carefully. right? But this is a weird substitution. So yes, we've covered it. Let's now forget about it. Yeah? And I hopefully have convinced you that I'm not pulling these things out of my rear end. That's where they come from. Right? Let's now forget about it. Not going to do this one. Yeah? Let's move on to the next one, which is integration by partial fractions, or partial fraction decomposition, or partial fraction expansion, whatever the textbook is, whatever textbook you're looking at is. Right? So this is how we handle rational functions. So remember, rational functions are just ratios of polynomials, and these can be very nasty to integrate. Right? Partial fractions is essentially, everyone knows what common denominator is, yeah? Back when you first do fractions in algebra and all that rubbish, you get sum of different fractions, and the first thing you've got to do is give it a common denominator, yeah? We all know how to do that, I would hope. Yes? Right? Partial fractions, or partial fraction decomposition, is exactly like common denominator backwards. So instead of getting a sum of all these different fractions and writing them as a single fraction, we want a single fraction and we want to split it into its parts, right, into separate fractions. And the hope is that all of those can be integrated. Right? So it's called partial fraction decomposition. Now, let's say I asked you to integrate that. Right? Now, you've basically got no choice but to try, let u equal the bottom and hope the derivative is the top. Right? So now the derivative of the bottom is 2x plus 1. I had to think about that. Right? Which is not, now of course if the top was 2x plus 1, life is good. Right? But it's not. It's x plus, no, it hasn't worked. Right? What do we do now? At the moment it looks quite formidable. Can't do it. But if you notice that you can write that x plus 5 and x squared plus x minus 2 as the sum of those two fractions, minus 1 on x plus 2 plus 2 on x minus 1. Right? And this is the sort of problem, when you first do fractions in algebra, the classic question you would have given is write this as a single fraction. So you would have gone from here to here. You know? Give it a common denominator, off you go. What we're doing is backwards. Right? And the thing is, writing it like that I can easily integrate. Right? They're just logs. Yeah? But it's hard to see how do I get that? How do I do common denominator backwards? Right? That's basically what we're asking. Right? And there's a specific algorithm that we use to do it. Provided we follow the rules, the algorithm is guaranteed to work. Right? So in general, we have this problem. We would like to solve the following problem called partial fraction decomposition or partial fraction expansion, or just call it frickin' partial fractions, make life easy. Right? Given a rational function, so ratio of two polynomials, where the degree of the top is strictly less than the degree of the bottom. Right? That's the first thing to check. Right? Where the degree of the polynomial at the top is less, not less than or equal to, less. Right? These are polynomials, the degree is always an integer. Right? So if the degree of the top is less than the degree of the bottom, you want to write it so it's the sum of several fractions. Common denominator backwards. That's the easiest way to think of it. Right? No, so where the polynomials on the bottom either have degree 1, right, so they're either linears or they're quadratics that don't have any real roots. We're not interested, we know now of course all quadratics have 2 roots, sometimes they're complex numbers. Some textbooks will do partial fractions with complex numbers. Don't do that. Don't do that. Right? It makes the life much harder. Right? So by irreducible we mean no real roots. So if you had an x squared plus 1 on the bottom, don't write that as x plus I times x minus I. Right? Because that's not going to help. Right? That'll make life harder when we've got to find the coefficients. We're only interested in real values here. Right? And as I say, basically it's like common denominator backwards. Now, what happens though if the degree of the top is greater than or equal to the degree of the bottom? Well, in that case, we need to use polynomial division first. Right? Right? So if the degree of the top is greater than or equal to the degree of the bottom, we use polynomial division first, right? Now, I'm assuming we've all done polynomial division before, but some of what we've found is that at school you're taught a thing called synthetic division. Anyone ever heard of that? Yeah? That's crap. Right? Synthetic division does not work in general. Right? So it's not a good method to use. It's better to use the full method. Now, this is one of those things where it's easier if you watch me do it from beginning to end. Right? So I'm going to redo this one by hand, right, to show you what's going on. It's very straightforward, right? But it's one of those things that's easy to see. Why isn't that light very... All right, so let's just do this one first. That's better, isn't it? Right. So let's say I've asked you, for example, to integrate this. Right, now if I ask you to integrate, that's nasty. Right? That's a nasty thing to integrate. So when you've got a rational function and a simple substitution is not going to work, which is definitely not going to work in this case because the top and the bottom, their derivatives aren't linked in any way, we have to use polynomial division first. I can't use partial fractions because the rules we're going to go through for partial fractions only work if the degree of the top is less, strictly less than the degree of the bottom. We've got to order 3 at the top, order 2 at the bottom. The rule won't work. Right? You'll get gibberish as your answer, which is a sure sign something's up. Now, we go back to basically what is a fraction. When we write that, what we're actually saying, remember, is that we're essentially, that big fraction is divide by, isn't it? Right? When we write a half, what we mean is what is 1 divided by 2. Right? So this is actually 2x cubed minus x squared minus 6x plus 11 divided by x squared plus x minus 2. Right? So what we do is we go back to old school divide by symbols. Right? What will happen is, you know, when you do division back in primary school, whatever, it's, you know, quotient plus remainder divided by divisor. Yeah? So, yeah, when we write 7 on 2, yeah, at university we write that as 7 on 2 or 3.5 if you want, right? But in primary school it's 3 plus a half, isn't it? 3.5, right? So the quotient plus remainder divided by divisor, right? And when you first do it, not that you would ever do this, but you know, you're basically dividing, what did I say, 7 on 2. So 2 into 7, you do, well, there's 3, that's 6, leaves remainder 1, so you say it's, right, 3 plus 1 over 2. Yeah? Everyone remember doing this years and years and years and years ago? Same idea. What you do here with polynomials, though, is you look at the highest power underneath the divide by symbol, which is 2x cubed. So 2x cubed divided by the highest power of what you're dividing into, which is x squared. 2x cubed divided by x squared is x, isn't it? No, it's not. It's 2x. Yes. All right? So you write, and usually we line them up, like, not that it really matters. Then what you do is you multiply this times this and write this underneath. All right, so that's just 2x times x squared plus, and you subtract. And what this does, the point is it wipes out the highest power. Minus x squared minus 2x squared is minus 3x squared. Minus 6x minus 4x is minus 2x. 11 minus nothing is 11. Yeah? Then repeat. Minus 3x squared divided by x squared is minus 3. Multiply this by minus 3. Subtract. That leaves x and you're done, right? Because now what the remainder is order less. So you can now say that this equals quotient plus remainder, right? So if you gave that a common denominator, you get back to where you started, right? But notice what's happened now is that this bit over here now has degree of the top is less than the degree of the bottom. So now I could use partial fractions on that, right? So that's the first thing to check, right? That the degree of the top is less than the degree of the bottom. There are other techniques to do this. As I said, synthetic division doesn't always work. Technically, this synthetic division thing, it only works if you've got linear. So if you're dividing by, say, just x minus 2, it'll work. But as soon as you've got an x squared in there, it don't work. Right? And basically, in the lecture notes here, what I've tried to do, as best I can, is... is colour-coded to show you the working. Right? So yeah, so that's basically, you see, doing 2x cubed divided by x squared is, I've tried to colour code it so you can match up. It's one of those things that's easy to see. That's what we do if the degree of the top is higher than the degree of the bottom. There's other ways to do it as well. If you're unsure, if you've got your own way and you're unsure if it always works, show it to me and I'll tell you if it's all right or not. Right? I mean, to be perfectly honest, this is not the way I do it. Right? I do it a different way, but no one likes my method, so I never show it. Right? Anyway. Right, but let's say for the moment now we've got to integrate a rational function. So if now we've still got the problem. If I ask you to integrate the first bit, the 2x cubed minus x squared minus 6x plus 11 over x squared plus x minus 2, I can integrate the 2x minus 3 bit. Oh, easy. That's x squared minus 3x. But the next bit, I still can't do. Right? I'm still stuffed. Right? Now, but common denominator backwards, because this is what I was showing here. This is the same as this bit. If you notice that this equals this, that I can integrate. Right? But how do I get this? How do I know? Right? Well, we follow some rules. When the degree of the top is less than the degree of the bottom, there are several cases which have logical extensions, but the algebra will get ridiculous. Right? So we usually stop at a certain point. If the denominator on the bottom has distinct linear factors, right? So this one up here, the x squared plus x minus 2, that factors to give what? X plus 2 times x minus 1, right? If you factor the quadratic. So that one has distinct linear factors. Then the rule says that when you've got distinct linear factors, every one piece will be spat out with a fraction with a constant up the top. Right? So if there are k linear factors, it'll spit out k terms. Right? Each one with an unknown constant up the top. So in this, the lowercase numbers are known from the function. The uppercase ones are what we've got to find. In the lecture notes, I use A1, A2, A3. When I do it by hand, I just use A, B, C, D. Right? It makes no freaking difference what you call them. Right? Next question is, how do I find the constants? Right? But what this is saying is these constants are unique and they are guaranteed to exist. Right? All we've got to do now is find them. If the denominator has a repeated linear factor, so let's say the denominator is, say, x minus a all squared, that will spit out two terms. One with a constant over x minus a plus another one with a constant over x minus a all squared. So if it was ordered 7, it would spit out 7 terms. And you'd have to then find 7 constants. I ain't going to be that mean about it. If the denominator has a quadratic that you can't factor into real roots, something like x squared plus 1, right, then those terms will spit out a unknown linear function up the top. Notice the pattern. This one is a linear. One order less than linear is a constant. Right? This one's a quadratic. One order less is a linear. Right? So if you wanted to keep this going, let's say you had a cubic on the bottom. We ain't going to do those ones. let's say you did, you'd have an unknown quadratic up the top, right? And these, you follow the rules and these constants are guaranteed to exist. If they don't exist or they're not unique, you're doing something wrong, right? To follow the rules, it's guaranteed to work. Now the unknown constants, what you do is you then do common denominator again, right? So you put them all back together again and you'll get an equation that needs to be satisfied for all x, not just some x. Right? And then you find them either by substituting in convenient values of x or equating coefficients. Right? So basically this idea is if you're saying two polynomials are equal for all values of x, then they must be the exact same polynomial. In other words, they have the same coefficients. Right? Right? So you either equate coefficients or you substitute a convenient value in both sides. As a simple example, let's say you've got the case where you've got to find A and B, capital A and capital B, such that AX plus B always equals 4x plus 3, no matter what the value of x. This one's easy, isn't it? Right? You either equate coefficients. Well, the coefficient of x on the right is 4, and on the left it's A's got to be 4. Right? The constant term on the right is 3, the constant term on the left is B's got to be 3. Or you could do it this way. Well, if I say this is an equation that has to be true for all x. So if I plug in x equals 0, I immediately get B is 3, don't I? And then I can substitute in any other value of x I like and get A. Right? So which method you use depends on the problem and depends on which one you prefer. Right? And you can combine all of these rules together. Let's say I asked you to integrate this. I ain't gonna. Let's say I did though. Right? Right? Now notice that the degree at the top is 2, the degree at the bottom is 2 plus 1 plus 4. So what's that? That's order 7 if you expanded it out. Don't do that. Right? But if you did, it would be some x to the 7 plus some other rubbish. Right? Notice you've got a repeated linear factor, and an irreducible quadratic of degree up to the power 2. So that means that partial fraction decomposition would look like this. Right? And you'd have A, B, 1, 2, 3, 4, 7 constants to find. I ain't going to be that mean. Right? But the key is though A, B, C, D, E, F and G will exist. And this you can integrate, kind of. That's easy. That's a log, isn't it? Right? That one, well, that's basically like a b times u to the minus 2. Easy. Another log. This one, bit of thought. I'll go through that in a sec. That one, hell. Right? So I can integrate that one, you can't. Right? It involves functions you've never heard of. You remember when I showed you that comic and one of the things was what the heck is a Bessel function? That one's a Bessel function. Right? But Bessel functions always pop up when you're doing integrals like this. Right? So this one, yeah, when we're done, you can integrate up to here. The last term, that one's a bit tricky to integrate. Right? That's not one I expect you to do. As I say, it involves functions you've never heard of. But in theory, we could do it. We can at least do the decomposition. Let's go through an example. This is one of those things that's easiest done by, when you watch me do it. Right? So let's actually not worry about the rest. Let's say I've asked you to integrate this. Right, we see the degree of the top is less than the degree of the bottom. Actually, no, before you do that, you try a substitution. If I let u equal x squared plus x minus 2, because that's basically the only thing to try, all right, and fingers crossed, it cancels with the top. It don't. Right? If the top was 2x plus 1, right, so for example, if this question was... Anyone got more paper? Anyone got a... Can I steal some paper? I've realised I'm getting... Can I steal some more paper off someone? I'm going to need more than that. Oh, or is that all right? Oh, no lines. Awesome. I love no lines. Now, if I ask you to integrate this, right, you can see what's going to happen. Done. Remember, you don't have to do it as fast as me, right? I'm just trying to illustrate a point. But if the top is anything else, this doesn't work, right? So if we go back to the one we were doing, this is not going to work, right? So what we do first, though, is we can use partial fractions, common denominator backwards, right? So what you do, now the bottom, x squared plus x minus 2, that's a simple quadratic that factorises to equal, right, we all should know the trick by now. If it's a monic polynomial, quadratic, in other words, there's a 1 in front of the x squared, what multiplies to give minus 2 and adds to give 1? 2 and minus 1, done, yeah? Now, so this one we've got two distinct linear factors. So the rules say that there is guaranteed to exist two constants such that I can write it like this. Then they're guaranteed to exist. I've just got to find them. Then what you do is you go, now give this a common denominator again. All right, so, you know, typical common denominator or cross multiply, however you do it. Right? Now, of course, the bottoms are already the same. Duh. Right? So what you've got here is an equation that says you're looking for constants A and B such that the numerators... Now, this is not an equation to solve for x. This is an equation you're saying is true for all x. Right? This is an equation to solve for A and B. And x is meant to be anything. There are two ways to go. You can either equate coefficients or pick convenient values of x. Right? Now, the convenient values of x are staring you in the face, aren't they? If I substitute x equals minus 2 into both sides, I'm going to get A, aren't I? Done. So when x equals minus 2, I get done. And if I substitute x equals 1, I get B. Ooh, awesome. Right, done. The alternate way to do it is, because sometimes you won't have convenient values of x, some textbooks recommend doing complex numbers. Don't do that. That's a silly way to do it. Right? Alternate way to do it is if you expand this out and collect like terms, so write it as a polynomial, then equating coefficients tells you, well, you must have a plus b must equal 1 and 2b minus a must equal 5. Two equations, two unknowns. You can do it that way. Those of you who are doing 1012 or are comfortable with matrices and linear algebra, knock yourself out. If you want to do it that way, I don't mind. Right? Perfectly fine. Right? What I normally do when I solve these is always do convenient values of x first because it's easier. Right? Another thing is if you want to check your answer, plug in another value of x and make sure it works. Right? So for example, if you're not sure, because what have we basically got? I found that a is minus 1 and b is 2. So this now basically says that you can plug in another value of x and make sure it works. Avoid 0 and 1 because they might hide other problems, because anything multiplied by 0 is 0, right or wrong, and 1, anything multiplied by 1 just gives itself back. Pick something else. So, yeah, what have we used? We used -2 and 1. Let's use 2. If I plug in x equals 2 into both sides, I get -1 plus 8. So I get 7 on the left, I get 7 on the right. Right? The chances of it being, not working just for that. Right? Remember, this is an equation to solve for all x. Right? Once you've got the a is -1 and b is 2, now what you've got is, now instead of integrating this, you've now got something much easier. Those you can integrate, they're just logs. Right? Do a simple substitution if you need to, but by this stage you should all recognise that these are logs. Some textbooks will make you join the logs. I don't give a crap about that unless I specifically ask you to. That answer is fine. Okay? Linear factors are actually the easier ones. So, right, so the ones that are harder are the ones with irreducible quadratics, right? How are we going for time? I'm going to do more examples in the next lecture anyway, but there's something I wanted to illustrate here. Now, recall that the rules we've got. Right? Now, we're only going to worry about these 3 cases. So I'm never going to ask you one that's got a higher than cubic on the bottom, because they are very nasty to integrate. Nor am I going to ask you one that has a irreducible quadratic squared on the bottom. Right? Also, you'll get a term that's too hard to integrate. Right? So, but you can see, if you follow the rules have a logical extension, right? Because you follow the thing where quadratic, unknown, linear. If you had a cubic, you'd have an unknown quadratic. If you had an order 47 polynomial on the bottom, you'd have an unknown order 46 at the top. Not that you'd ever do that, right? Certainly not by hand, right? But if these are the only cases we can do, these terms, they're logs, aren't they? Done. Log, and these are u to the -2s, u to the minus, easy, yeah? How would you integrate this bit? Right? You're assuming that x squared plus bx plus c has no real roots, right? That you can't split that up anymore. So how would you do that one? Well, there's 2 ways to go. There are 2 ways to do it. If it was, you can make the top be the derivative of the bottom, so it becomes a log, right? So that's c1x plus c2. Right? Think of that as c1x all over x squared plus bx. Let's assume for the moment b is 0, right? Just to get the point across. Let's say that's just x squared plus c on the bottom. Okay? So if I split it into 2 pieces, so I've got a c1x over x squared plus c, that's a log because the top is proportional to the derivative of the bottom. But the constant over x squared plus, how the hell would I do that? Well, this is where the formula sheet comes to the rescue. Ooh. Right? So that means these ones will become inverse tans. Right? And remember what I said, that this thing actually has a lot more information than you realise. And this particular one, this basically says that the integral of 1 over 1 plus x squared is inverse tan plus c. Right? So that's what I've said here. But that integration formula is basically on the formula sheet, and you'll need that one when you have quadratics. Okay? Right, since we've got time, I'm going to do more examples by hand, but let me try and... I want to do one of the harder ones. I want to do this one by hand. You sure it's all right I use all this paper? Thank you. I can bring you a nice fresh pad in the next lecture if you're worried about finances or whatever. All right? Right, let's have a look at this one. Let's say I asked you, because this example basically brings it all together. Now I've asked, basically we've got to integrate this. Now it should be obvious at this stage that no substitution is going to help. No, not a chance. Right, not a chance. Right, but it is a rational function. We've got an order 1 polynomial up the top. If I expand it out the bottom, it's an order 3. Right, so I can go straight to the partial fraction rules. Notice, however, that the x squared plus 1 can't be factored into real factors. Yes, technically you could write that as x minus I times x plus I, where I is the square root of minus 1. Some textbooks and websites do that. Don't do that. Right? That's just going to make life harder, because then you'll have fractions involving complex numbers. You've got to realise the denominator. Can't be bothered. Right? Don't do that. So this one I can't factor, but what the rules say is we have a linear factor times a irreducible quadratic. Right? So the rule says that the partial fractions rules say the linear factor will spit out a term like that, where a is a constant. The irreducible quadratic will spit out a term that has an unknown linear up the top. This is the first common mistake everyone makes. If you had written that not bx plus c, but either as just bx or just c, what will happen is you can't find the b or the c, or it's not unique. And that's because you're not following the rules. Right? It might turn out that one of the b's or c's is 0, but you don't know at this stage. Right? So follow the rules. Note the pattern. Linear on the bottom, 1 order less up the top, constant. Quadratic on the bottom, 1 order less, linear, which has 2 terms. You know, if this was x cubed plus 1, I wouldn't give you that one, but let's say it was, then the term would be bx squared plus cx plus d. Yeah? But we won't do those ones because those are awful to actually integrate. The key is we're following the rules. A, B and C must exist. The way we find them is we give this a common denominator. Right? As I say, the easiest way to think of this is common denominator backwards. Right, now the bottoms are the same, so the tops have got to be the same. So in other words, we must have for all x. Right, all right. Now what? Now I've got to find the damn constants. What could I substitute in to get a quickly? Well, if I plug in x equals 1, I've got a, haven't I? Done. Yes? Because that'll annihilate the second term. Yeah? So a's got to be 2. Has to be. Let's now rewrite this with now what I know. One down, 2 to go. What could I find next easily? What would I do next? How could I find C? What would I substitute to find C immediately? 0, wouldn't I? Right, because this bit will disappear. Right, so if I plug in x equals 0, I get I've got C. Awesome. Oop. Are there any other convenient values? No. But does it matter? I could pick any value I frickin' like. I've only got one left. Doesn't matter. I can pick anything. This is supposed to be true for any x. Well, I've used x equals 1 and x equals 0. Make life easy. Why don't we use minus 1? So what do we get? We get worried? Pick another value. If you get a different value of b, something's up. It's got to be unique. Right? Or what you could do instead is you could expand this out and equate coefficients. I'll show you why I don't like that method, unless I have to. If I expanded this out, I'd get, again, don't do it as quickly as me. Hopefully I haven't stuffed that up. Let me just check since I've got everything now. A plus... hang on, what's B? Alright, so that's telling you that, well, A plus B's got to be 0 because there's no x squared over the right, minus B plus C's got to be 4, and A minus C's got to be 0. Because technically what you've got is over the right is 0 times x squared plus 4x plus 0. 3 equations in 3 unknowns. Yeah, I can't be bothered doing that. But if you're doing 1012 linear algebra, you want to do it that way, be my guest. All right? Once you've got the constants though, we've got basically, we've shown. So what did we have? We had A is 2, B is minus 2, and C is 2. Okay, now what? We haven't integrated the damn thing yet. How would I integrate the first? That's just a log, isn't it? Easy. Yeah? What about the second bit? What we do here is split that up like so. Now the integral of the first bit, that's just log, isn't it? Right, so the first bit just integrates to give 2 times log of x minus 1. Look carefully at the second bit. Well, the top is the derivative of the bottom, log. Right, so the second term is log of x squared plus 1. What about the third bit? Right, that's where we use our inverse trig one. Right, that's where we use this. Right, so straight away this integrates. Done. Right? So these ones are a lot of work. Right? Now I'm going to do a few more examples in the last lecture. Right? What I would like though first is, instead of actually doing the integral bit, just concentrate on doing the partial fraction decompositions and following the rules. So if you have a look at a couple of these examples, imagine I haven't asked you to do the integral, that I've asked you just to separate these by partial fractions. right, and have a go in finding the constants and that sort of thing. And I'll keep talking about the examples in the last lecture this week, all right, because we are out of time. All right, but we'll leave it there. Thank you for the paper. Oh, that's the last page. Oh, sorry.
Right.
Thank you very much. I'll have to remember to bring a new pad of paper next time.